Alright, so here is lesson 6.H.3, and we're going to do, this is a lot like the ones before to start off with. There's just a few amplifying questions. There's an image. We're going to do some transformations of that image. And like I have shown many times before, you start with a point table of J, K, and L. This is in this quadrant here where all the x's are negative and all the y's are positive. So that's what you should expect to see when you transcribe these. So J is -5 and 1. K is -3 and 4. And L is -2 and 2. And that is my first set of starting coordinates to work with. I'll shift to green for my first transformation. My first transformation coordinate comparison is this. My x's and y's flop, so I know it's a 90-degree rotation. The x is negative, so it's going to rotate clockwise. So I'll put my new x and y coordinates are going to be driven x, comma, negative y, negative x, like that. Remember, the negative x does not mean that they turn negative. It means that the x coordinates change sign. So my new x column x values are pulled from the old y points. So they're going to be without changing sign. So 1, 4, and 2. My new y values are the opposite signed old x values. So they'll be changing from -5, -3, and -2 to +5, 3, and 2. 5, 3, and 2. So these all will stay on. They're going to rotate from this quadrant where the x's are negative and the y's are positive to this quadrant where everything is positive. So let's rotate J from this point to 0.15. So J is going to rotate about origin of 1 to 0.1, 5 to J prime. We'll rotate point K from this point to 0.43. So 0.4, 3 to become K prime. Then we'll rotate point L from its current point to 0.2, 2, right there. This will be point L prime, and we'll connect the dots with a straight edge. And there we are. Connect right. There we go. Now we have our rotated point. Now if you looked and you connected each point through the origin, you would notice that each one of those is a 90-degree angle. Okay, so now we'll move on to our next coordinate, our next transformation, and this is a dilation of a scale factor of 3/2. So this is 3/2 is greater, 3/2 is greater than 1, therefore it's going to grow. So you can expect this to grow. So our new x, y coordinates, we're going to multiply the old x, y coordinates by a factor of 3/2. So easy way to do that, 3 divided by 2. 1.5 is easier to type in the calculator than 3/2. It's not some weird long decimal. So I'm just going to multiply each of these x and y values by 3/2. The x's and the y's don't flop. The x and the y's stay in the same spot, right? They don't flop. So I'm just going to multiply each one by 3/2. It's easier to write up there. Okay, so this is 1 times 1.5 is 1.5. 1.5 times 4 is 6. 1.5 times 2 is 3. 1.5 times 3 is 4.5. And 1.5 times 5 is 7.5. So now I have these new points. So I'm going to dilate 1.5 and 7.5 about the origin. Right, because remember these are just distances from the point of dilation, center of dilation, which is the origin. This is just the distance of this point, and I'm going to dilate it by a factor of 3/2. Right, so this is the new x and y point. If I expand it by a factor of 3/2, so 1.5 and 7.5 puts me right at the extent of this. That's going to be j double prime. I'm gonna expand k from here to here by a factor of 3/2. So that's going to be now going to be 6 and 4.5. So it's going to be like 4.5. That's k and a half. That's k double prime. And then I have this one's going to go from 2. This distance is 2 for both the x and the y value. So it's going to be now expanded to 3 for both the x and the y value. 3 and 3 for x and y respectively. So that's L, put it right here, L double prime. Connect the dots, make a triangle. I'll do this one first so I'm not dragging across my inked lines. And after each dilation, I like to grab another colored pen, and you can line up your dilated points. And if you did it right, your dilated points will, if you extend a line through your dilated points, they will intersect at your center of dilation pretty easily, like so. That's a pretty good indication that it was done right. Okay, so that is the third or the second set of dilations. Okay, and I'll shift to purple, I guess. Well, let me close off this set here. Okay, and now my third set of transformation is going to be, let's see, my x's and my y's stay the same, so that means pretty indication that it's going to be a reflection, unless that one is negative, but one of them is negative, so this is a reflection, and then y changes. So that means it's going to go from here to here, so that's going to be a reflection across the x-axis, so it's going to be x comma negative y. X comma negative y. So my x values all stay the same, 1.5, 6, and 3. My absolute values of my y stay the same, but they change from whatever they were to the opposite of what they were. So they were positive, and they're going to change to negative. So negative 7.5, negative 7.5, negative 4.5, and then negative 3. We plot these. Some mistakes that are made during this transformation is they just shift off the line that you're sliding it along, or you don't land on the right y value in this case. So J, make sure you're picking the right orange one. J here, we're going from 1.5, we're going to go all the way from 1.5 to 7.5, all the way to the opposite 1.5 and 7.5 to make J triple prime. Okay, and then L is going to stay on 3 and go to the opposite -3. Make sure, see, I almost wanted to like the wrong one. So carefully go from 3 to -3 on 3 of the X value and make, that's going to be L triple prime. I'm trying to have a little bit of foresight and think about where I'm going to label my point here. Okay, and then K. Oh, sorry, that should have been okay. And then K is 6, and I'm going to stay on 6 and write it all the way to -4.5. 6 riding it to negative, that's -4, -4.5. That's going to be K triple prime. Right, now I'm going to just write these here. And there we go. There we go. All right, so that's real similar to the last part of the unit. I'm going to zoom out for a second so we can answer the rest of these. All right, so indicate the relationship for the resulting image comparison. All right, we're comparing all of these to the initial pre-image. The initial pre-image. Prime, double prime, so prime, double prime, and triple prime. And triple prime. Okay, so prime and double prime, they're the same size and shape. Okay, so the same size. You're really just looking at the same size. They're congruent. They are congruent. But after the after the dilation happens, right, they're only just similar. Both of them are just similar, right? So you can only say after the dilation, as compared to the original one, similarity exists. Now, if you compare this one and this one, like right here, these two are congruent, right? Because this is a rigid transformation, right? Between here and here, that's just a reflection, right? But between this one and this one, they're not the same, right? They're similar. The angles are congruent, but the line segments are different lengths. So that is a similar. That's a similar comparison. Okay. So then here we go. Patty paper is helpful on this one. Pause it while I go get some, so you're not waiting. Okay, so here we have two triangles, ABC and DEF. And it's saying that, assume that A and B, and the ratio of A and B and D and E and B and C and E and F and A and C and D and F are equal. So we know at least that these are similar, right? It shows that they're similar, but are they congruent? I don't know. I wonder if they're congruent. I mean, maybe this ratio is 1 to 1. If this ratio is 1 to 1, then do we need to do a lot of dilation? No, right? So let's see if we actually even need to do a dilation, right? So it could be trying to be tricky here and saying, well, you don't need to do a dilation because if this ratio is 1 to 1, now how do you figure out if the ratio is 1 to 1? Well, I'm going to see this A to B, the D to E is, I'm going to see what the X to Y change is, right? So, the X to X change. See, A to B, that's the change in 2 to -5, -2 to -5, that's 3. And then D to E's change is 3 to 0. That's a negative. That's a ratio 1 to 1 there, right? So I'm like, well, maybe I'm having suspicion that there's no dilation here, right? And then I have a change of F to E, right? E to F. Let's see, my change in Y here is 1 is only 2, and my B to C, my change is only 2. So something's fishy going on here. They're saying that they're similar, but I bet they're congruent. Right, so I probably don't even need to do a dilation here. I only need to do like a rotation maybe and a translation. And if that's the case, then all I need to do is like throw some patty paper on there, play with the patty paper, and then I should probably make this thing up and down perfectly so that I can. I don't like when they're like this on the. Okay, make sure my paper is square. So when I started doing that, you wondered why I started doing it like that. My patty paper wasn't square. Make sure your patty paper is square, maybe even center. So I'm gonna go ahead and like push that down and flatten it out. I don't like it when it's on the hump like that. And then I'm gonna line it up, and if all the line segments are the same, guess what? They're not only similar, but they are congruent. Because I got a sneaking suspicion that they are congruent shapes, and I don't have to dilate this stuff. Okay, so let's see. Well, maybe not. Maybe. Wait. Yeah, look at that. They are the same size and shape, but I flipped the paper around so I have to reflect it. So I'm going to have to reflect across the x-axis, or correction, the y-axis. So reflection across the y. Right, so if I do that, that's going to put y, it's going to put my value of a there, which matches up with d, at 1 and it was at 1 or 2 and -1. So it's going to put I only need to map 1 point on 1 point now if I'm just going to do translation. Because I mapped it, and I just need to, like, my reflection oriented it the proper way, and it's the same size, so I don't need to dilate it. So this orientation, I made it so that all I need to do now is translate it. So I only need to really figure out my change in x and my change in y with 1 point. So my reflection is x comma y yields x and y did the same, and my x values flopped, so that changed like that. Okay, and then because my a went from 1 to -2, so my a value went from 1 to -2, so my a value is now 2, 1, and it lines up. Its paired point is D, which needs to go to D, which is 0, -2. Okay, so my change in x, this is my final, this is my initial. Right, so my change in x, maybe I should put this down here or up there, and whatever. My change in x is going to be my final minus my initial. My change in y is my final -2 minus my initial, which is 1. So my change in x is -2. My change in y is -3, and that makes sense, right? Because I'm here, I need to go over 2, that's left 2, and then down 3. 1, 2, 3. Right, so my translation left 2, down 3 should be written like an algebraic expression. should be written x minus 2, y minus 3, like that. Okay. And now it's given that DEF is a result of, oh, look at that. Yeah, I did that. I didn't even read that. Okay. Well, it means that they're congruent, right? There's no dilation in this, right? The answer was all right here the whole time. Didn't even realize that. Okay. DEF is a... That's not true. DEF, ABC was a result of... Oh, yeah. D is a result of... Yeah, that's true. Yeah. Well, would you look at that? The answer was right there the whole time under my nose. Okay, so here we go. And then we have this this little given table here, right? It says that line, we have a triangle. Got triangle small here, TVR. I got triangle big here. Triangle big here is, I don't know, PVQ or PQR. Big and small, big and small are shown. Okay, don't think that they're similar that way because it just says and, so don't mistake it that way, right? But TV and PR, so TV, and PR. Okay, this is my large over small, small over large, and VR, and PQ or QR is my small over large, over large. Okay, I don't even know what the question is, but is it, I'm trying to say that this is enough to say that these two triangles are similar by angle. Well, the only thing in here that I know that shows that angles are similar are these vertical angles here. I got an angle here and here that are similar because of vertical angles with what is given in the given statement. So I have two angles, right? I have an angle here, I have an angle here, and I have two angles here, and that's not enough. Nope. Justification. I have two sides and an angle not in between those sides. It's not enough to meet those. It's not enough to meet the angle sides, and one angle. It's not enough to meet the angle similarity. Okay, so that's not enough. Okay, so the next thing is I have that PQ and VT. PQ and VT are parallel. Okay, I still have these two angles that are vertical angles, and then because these are parallel, if I extended these lines here and here and here and here, it helps you see it a little bit better. Well, I have these transversals, I call it transversal orange, and a transversal green here. I have two transversals here, and I would have this angle and this angle, which are alternate interior angles, and I have this angle and this angle here, which are alternate interior angles. So I got plenty to say that got two sets of alternate interior angles and a vertical angles are congruent. Therefore, angle similarity conditions are met. Alright, so that's that. I hope that helps. If you guys have any questions, feel free to ask.